How is elasticity crucial for sound wave propagation? Imagine shouting in a canyon and hearing your voice bounce back. That's because sound waves travel through the air by making particles vibrate. But what makes this vibration possible? It all comes down to elasticity. Elasticity is a material's ability to stretch or compress when force is applied and then return to its original shape once the force is gone. Think of a rubber band or a metal spring. When you pull or push them, they change shape but bounce back. This property is measured by elastic constants like Young's modulus and shear modulus, which tell us how stiff or flexible a material is. When a sound wave moves through a medium like air, water, or solid material, it causes particles to oscillate or move back and forth. For these particles to keep moving in a wave-like pattern, the medium must have elasticity. Without elasticity, particles would not return to their original positions after being displaced, and the wave would stop. In solids, sound waves can travel as longitudinal waves, where particles move in the same direction as the wave, or as shear waves, where particles move perpendicular to the wave. The speed of these waves depends heavily on the elastic properties of the material. The stiffer the material, the faster the wave can travel because the restoring forces act more quickly to push particles back to their original positions. Elasticity also plays a role in how well sound energy is transferred from one particle to another. If a material is very elastic, it can transmit sound more efficiently. This is why metals, which are quite elastic, allow sound to travel quickly and clearly. On the other hand, materials that are less elastic tend to absorb or scatter sound waves, which slows down or weakens the transmission. Understanding elasticity is important beyond just sound travel. It helps us detect cracks or damage inside materials. When a material is damaged or loses its elastic properties, sound waves don't travel as they normally would. They may scatter, slow down, or weaken, which can be picked up by special devices. This is how engineers find hidden flaws without destroying the object. If a material becomes permanently deformed or develops microcracks, its elasticity drops. This change affects how sound waves move through it. The waves may become weaker or change speed, indicating that the material is weakening or breaking down. So, in simple terms, elasticity is what makes sound waves possible. It provides the restoring force that keeps particles oscillating and allows the wave to move smoothly through a medium. Without elasticity, sound would not travel, and we would lose the ability to detect, listen, or analyze the world around us through vibrations.